All right then. Hello. Good morning. Talking about probability, and we're going to talk about compound events. Compound events basically means we've got a couple of things happening at one time. So we're looking at the probability that this happens, and this happens, and this happens, or this happens, or that happens. So there's lots of possibilities as we work our way through. Not that complicated. So the first thing is, say we want to know the probability that when we roll a die, we get a 4, or when we draw a card from a deck of cards, we get a 2. So we want one of those things to happen, both make us a winner. So what we first need to know is what's the probability that either one of those things happen. So we know that the probability that when we roll a die a 4 comes up is 1 out of 6. And when we draw from a deck of cards, the probability that a 2 comes up, well, there are 4 2s out of 52 cards. Okay? And so somehow we got to figure out what's the probability that one of those things or the other one happens. So we have a rule for that, and these are mutually exclusive events that if one doesn't make the other one not happen. Okay, that there's no overlap basically between the two things, rolling a die and drawing a deck out of cards. There's no overlap. They're mutually exclusive. And so when they are, we just take the two probabilities and we add them together. So in this case, we want to know the probability of a 4 on the die and a 2 on the card. We just take the probability of the 4, which is the 1 out of 6, and we add to it the probability of the 2 on the cards, which is the 4 out of 52, and we get an answer. And we can just use our calculator. We could do all sorts of fraction conversions, or we could just put in the calculator 1 divided by 6, which is 1/6, plus 4 divided by 52, which is 4/52, add them together, and we come up with 0.24, which we know to be 24, that's a 4%, 24.3%. So about 1 out of 4 times when we roll the die or draw a card out of the deck, we're going to get either a 4 on the die or we're going to pull a 2 out of the deck of cards. Okay? Now, if, for instance, we're faced with the dilemma of, well, we want to either draw a 3 or we want to draw a club, I'm sorry. Okay, so either a 3 or a club. One or the other when we're drawing out of a deck of cards. So the probability we draw a 3 is 4 out of 52. The probability that we draw a club, well, there are 13 clubs out of 52 cards. Okay, so we could just, using the rule from last time, we could just add those two together, correct? Or not so correct. Okay. The problem is there a 3 of clubs? Yes. So these two events are not mutually exclusive. So they could it's possible that we could get a 3 and a club at the same time. So when we try to calculate that, we do the same first part, the probability of A, plus the probability of B, but we've got to subtract in that probability of the overlap that both things can happen at the same time because these are not mutually exclusive events. So the probability that we got where are the two events? Probability that we got the 3 was the 4 out of 52. Okay. The probability that we got the club was 13 out of 52, and then we've got to subtract the probability that we end up with the 3 of clubs, which is only one of those, out of 52. And so we have 4 plus 13 is 17, minus 1 is 16 out of 52. Change it to a decimal, which is 30.7, so 0.307, which is 30.7% chance. Okay, so if they're not mutually exclusive, meaning that there's an overlap between the two things that are happening, then we've got to subtract away that overlap. Does that make sense? So this is my 3 of, it's supposed to be a club. There, 3 of clubs. Okay, so there's that. Probability of two things happening at once, and let's just let's see what fate gives us. What's the probability that we draw a 3 from the we roll a 3? So the probability that we get a 3, and at the same time when we draw one, we get a 2 out of our deck. So the probability of the 3 is 1/6. The probability of the 2 is still 4 out of 52. But we want them both to happen. Okay, so is it more likely that both things are going to happen? Less likely? If we add them together, it means that it's more likely that they're going to happen together. But the fact that we need both things to happen is slightly different. So in this case, we take the probability of A and we multiply it by the probability of B. So we're going to have 1/6 times 4/52. Okay, which when we multiply fractions, we multiply across the rows. So 4 out of 52, so 4 is on the top. 6 times 52, 6 times 50 is 300, so 312. Okay, 4 out of 312. We could reduce that. We should reduce that, maybe. But we should certainly change it into a decimal so that we have that other information as a decimal. That's 0.012, which percentage-wise is about a 1.2% chance that when we do two things, we roll a die and we draw a card out of a deck of cards, so we get those two things to happen. Okay? So back to our cows and bulls that we talked about in class on the other day. What's the probability that when we're trying to interview a hunter that got these, and we have the list of all the hunters, and we just randomly draw one out? What's the probability that we've got somebody that shot a moose on either October 20th or they shot a bull moose? Well, the total number of people that shot on October 20th is 34 out of 198. The probability that somebody shot a bull is 108. It's 108 bulls out of 198. And since these aren't mutually exclusive events, we could have shot a bull on October 20th. We don't want to count these 18 moose here, so we've got to subtract out the 18 out of 198 from there. Does that make sense? If we're looking, and we could add them, you can do the arithmetic on that. What's the probability that we draw somebody out to interview that either was got a moose on October 20th or the 21st? Well, on the 20th, we had 34 out of our 198 moose shot. On the 21st, we had 32 of our 198. Is there any overlap between the October 20th and 21st? Are these mutually exclusive events? These are mutually exclusive. We can't have shot, on the same day. So that would be, 66 out of 198, changed to a decimal, that sort of thing. Okay? And then what's the probability that we get somebody that was on October 23rd and they shot a calf? So October 23rd, calves. So there are only 2 of them on October 23rd, so that's 2 out of 198. Why didn't we multiply? I would say we could probably get the same answer if we were to take the probability that we shot somebody on October 23rd. Let's see if we can do this. Shot a moose on October 23rd is 26 out of 198. Sidebar. The probability that we shot a calf was 16 out of 198, and I'm guessing maybe if we multiply those two together, we might end up with the same fraction. 26 times 26 198 times 16 198 gives me a decimal of 0.0106. And what's 2 divided by 198? 0. Okay, so there's a little overlap. 0.0101. So it's got to be that we've got to account for that. So that's how that works. So we got a box, 6 blue tickets, 8 red, 12 green. You can read those. 2 tickets are drawn from the box. We want to know the probability that both of them are red. And down here is the key on this one. Are we putting the tickets back in the box after we draw them out? Do you have more than one chance to win? So in this case, we're not putting them back in the box, so we're going to do it without replacement. So first, we need to find the probability that the first ticket's red, and that's 8 out of 26. And then the probability that the second ticket's red, well, we're assuming the first ticket was red, so there's only 7 red tickets left, and there are only 25 tickets left in the box. So we want both things to happen, so we do 8 out of 26 multiplied by 7 out of 25. See how that works? Okay. Without replacing them in the box. The probability that we have a red one and a green one, well, there's 8 out of 26 red, and green is 12, so there's 12 tickets still in the box, but there's only 25 total tickets, 12 green, 25, so we're going to multiply those across. And the probability that neither one of them is blue, well, what's the probability that the first one's not blue? Well, there are, 18 not blue tickets. 18 not blue tickets out of 26. And then there will be 17 not blue tickets out of 25. After that, we multiply those two probabilities together. We'll get ourselves an answer. So if we're not replacing, our denominator gets smaller because we have less tickets in the box as we go. Okay? If we do the same problems with replacement, means that we draw a red ticket out and we put the red ticket back, we put it back in and we shake them around and we try again. Well, the probability that the first one is red is 8 out of 26. Probability that the second one's red is still 8 out of 26 because we took that red ticket, put it back in the box. Okay, see how that would work with the rest of these? Okay, probability of red and green, so we'd have an 8 out of 26 on the red, and a 12 out of 26 on the green because we're just putting our tickets back in the box. Okay, so that's the difference between with replacement, without replacement. We want to be able to keep that squared away. That's all I've got. Okay, so we're talking about compound probability, the probability of ands and ors, and that. I think is about all we've got to say. So do the best you can working through those, and we'll talk about it later. Give you some practice problems to do as well. Thanks for stopping by. Talk to you soon.